Hello, my name is Berend Smit, and we continue our lecture on advanced molecular dynamics simulations. We have now discussed the very wrong way, just an instantaneous update every single time step by rescaling the velocities. We have discussed the Anderson thermostat, in which we make collisions. Or collisions is basically after a certain time, we select a particle that of its velocity is taken from the Maxwell distribution that corresponds to the temperature we're interested in, and that is the Anderson thermostat. And we see that it's actually a very rough way of perturbing. A rough way in which we perturb the dynamics of the system significantly. And there have also now been methods in which we perturb it more gentle, and that is what we would call the Nose-Hoover thermostat. But in order to understand that, it's important that you know a little bit about how to write dynamics, classical dynamics of movements, from Lagrangian and Hamiltonians. And that is that part we start with before we can discuss the thermostat, because we need to assume that you know what a Lagrangian and a Hamiltonian is and how to derive the equations of motions from them. And this is not typically done in chemistry or chemical engineering classes, so that's why in this part we give an intermezzo in which we review that, and then the next lecture will be on how we use those Lagrangian and Hamiltonian to do dynamics at constant temperature in the canonical ensemble. So this is more a recap of classical mechanics. Okay, so what is the idea of the Hamiltonian and the Lagrangian? And that is, the basic concept of a Hamiltonian and Lagrangian is, can we formulate the equations of motions independent of a coordinate, of the coordinates. So an independent formulation, so irrespective of which coordinates you use, you would like to have a formulation of Newton's equations of motion that isn't dependent on whether you have x and y coordinates, but you can have polar coordinates or coordinates that are more natural to describe the dynamics of a system. And the way to do that is through the action. So what is that? And that is that the equations of motions, so solving Newton's equations of motion is equivalent in finding a path. And that's what I will read it here. The equations of motions give the path that starts at t1 at a position xt1 and end at t2 at a position xt2, for which the action takes the minimum value. So what is the action? The action is the difference between the kinetic energy and the potential energy, and then the action is defined as the integral over time from t1 to t2. And what is the statement? If you the path, so the path for which this action takes its minimum value gives you the equations of motion. So you see how this path you can describe in any coordinates. As long as you guaranteed, you make sure it's the minimum one, you get the equations of motion. This is something I give without a proof, and if you are interested, you need to look at a textbook of classical mechanics. So this is the statement, and that is a statement, we're just going to look at it to familiarize yourself of how you can look at these kind of things. So what does it mean in a diagram? So here we have our starting configuration. Here we have our end configuration, and this is a typical path. So let's now assume that this is the true path. So what you see here, we have a trajectory. Here we have another trajectory. And what the statement is, that any path, any trajectory you can think of that is not corresponding to the true solution of the equations of motion, you can see that it has a higher action than the action of the true path. And that is the idea. So as long as you can keep trying to draw all kinds of paths, as long as you don't have the true path, you will always see that it's it has a higher value. So it's sort of important to find a path for which the action takes its minimum value. Okay, so let's see whether that makes sense. Let's see whether with this one we can derive the equations of motion of the most simple case, for example, a particle in vacuum. So a particle in vacuum, no potential energy, we only have kinetic energy, and we probably know the solution. If we have a particle in vacuum, it will move with a constant velocity. Okay, let's see whether such a simple result can be obtained from such a complex formulation. That's always interesting to see. Why make life easier if I can make it more complicated for you? I won't hesitate, as you may know already. Okay, so the action for this particle, you can see, is the kinetic energy minus the potential energy, and we only have here kinetic energy. So the action is basically the kinetic energy integrated over that time. Okay, so what we now can do, and this is a typical trick which we used in these path integrals. And so this is an integral over a path, so this is what we call the mass path integrals. So we assume a particular path, and then we try to prove something on for this. So what is the idea? So we have our velocity at a function of time. We say it's the average velocity plus a deviation from the average velocity. Okay. So if we substitute that, we basically say, we just substitute this in here and we look. And you see, if you write it out, you get different terms. So you have the this part squared, and if you take it, so you have three terms. This part squared, 2 times this one, and this one squared. So let's look at the first term first. So the first term is only this term, and then it's a constant, so you can take it out of the integration. So you get here t2 minus t1. You get this term. Then we have the term where the 2 is coming out. You get the average velocity times the deviation of the average velocity and this term. Now, if we now focus on this term, so what is this term? And that is basically the deviation of the average velocity over this time. So if you just substitute this equation, you basically have the velocity at time minus the average velocity is this, but this is by definition 0, because that this divided by the time interval is the average velocity almost by definition. So you see that this term is 0, and we are left with this term here. So you basically have the action of the average. The action associated with the average velocity, that is this term, a term that is 0, and a term that, interestingly, that is always larger than 0. So hence, this action takes its minimum value if eta t equals 0. And that is actually telling me, so the solution of this one is, since this was arbitrary, you could do this for any function, this needs to be 0 and the velocity is constant. This is exactly what we would have expected for a free particle, but we have it definitely now derived in a more complicated way. And that is always a good achievement. So this is the solution exactly as we expected. Okay. So there is a formal way of solving this, and that is called the calculus of variation. So what we do is we define the path as the sum of the true path and the deviation of the true path. Now, it's a little bit similar to what we have seen with the velocities, but now we do it with positions. So we write the actual paths the particle takes. So this is a path a particle takes. This is the true path the particle takes, the solution of the Newton's equations of motion, and this is the deviation of the true path. Okay, and then the action is then the difference of the action is the action of this path minus the action of the true path. Okay, So the true path is the one for which S takes a minimum value. So this is basically the assumption. So what we now assume, we know the initial and the final conditions. So we know exactly where the particle starts and ends, which basically means that at the boundaries, these two terms are zero. And that is something we can always do. And what we also going to assume is that we have a good guess of the true path. So this is a relatively small perturbation of the true path. So we basically look at small variations around the true path. Okay, so if we now look at the kinetic energy, we substitute this expression for v dot, and you basically is x dot, is the time derivative, and you see we include the path and the true path. So we are going to assume that this term is small, so we approximate it by this. And for the potential energy, we're going to also assume that we can have the potential energy associated with a true path and a deviation from that where we have the eta. Okay. So we can now write for the action, which is the difference between the kinetic energy minus the potential energy, this term. You basically see this is from the kinetic part and this is from the potential path, and it's again here we assume that we have only a small deviation, and the same here. So if we now look at the different terms, we can collect them. So here this part and this part is the action of the through path. Then here we have a term with eta dot, and here we have the term with eta left, and this is here. And it would be interesting, what you would like to do now is to make sure that for every path, this term is zero. So and then you need to have something where you have this part sort of in brackets and that one out. Then if this part is zero, it's always zero. But what we see here, this is eta dot and not eta. So we need to get rid of the eta dot and make it upgraded to eta. And the way you do that is with partial integration. So we need it in that form. And this is what you do with partial integration. So if you have a product of x dot and eta dot, you upgrade this one here and you downgrade this one. So this is basically what you see, but at the boundaries, we have said by definition that the eta is 0 at T2 and T1. So this term drops out, and we basically can convert this term into a term with x double dot and eta. And that is what we want to have. So if you now look at this, so if this term is 0, we have by definition a action that is minimum for all values of eta. So this is then the condition we have. And that is exactly what we call Newton's equations of motion. So mass times the acceleration is equal to the force on the particles. So this is the potential energy with respect to the position, and that is giving us the force. So you see, we can also make life much more complicated in the way we derive Newton's equation, from this concept of that the action takes its minimum value for the true paths, and from that we basically see Newton's equations of motion coming to appear. Okay, but we now have a formalism, and that is important, that is independent of our coordinates, and let's look at that. Okay. Before we give an example, and we can now reformulate the equations of motions in generalized coordinates. So what is the idea? We have two coordinates, which is the x coordinates with the Cartesian coordinates, but what we would like to do in more generalized coordinates that are much easier, they're much better fitted to the coordinate systems of our problem. So what we do is we define the Lagrangian. And the Lagrangian is the kinetic energy minus the potential energy, which we can write in terms of generalized coordinates in these Q variables. Okay, and then the statement is that the action takes its minimum value for the true paths. So what we're going to do is we're going to write in generalized coordinates that we have the true paths and the deviation, and the same for the velocities. So we see if we then write this term for the Lagrangian, we have the Lagrangian associated with the through path and two terms, one with eta dot and one with eta. And then the thing here is we need to upgrade this one to get it in this term, that we can put the brackets around here and get this here to be 0. So here we then do the action. You see the action of the true path, you get these terms, and we need to upgrade this one so we can have a term here which is between brackets. So the upgrade is like we did before, you get the double derivative of this one. Okay, so the way to do that is what we see in partial integration. So we take advantage of the boundaries that the eta terms disappear. So we basically have the time derivative here, and this is then the action. So this term needs to be 0. If this term is 0, then for every single independent of eta we have the true paths. So and this is as condition, and as a result we can now write the equations of motion by first defining a generalized momentum. This is a conjugate momentum that belongs to the coordinate q. So to the coordinate q we now associate, we define a momentum using this formula. It's basically this expression is simply the derivative of the Lagrangian with respect to q dot. And here we have now the equations of motion. So we have p dot is the Lagrangian with respect to q. This looks all abstract, but if we see an example, it gets a little bit easier. And these are the Lagrangian equations of motion. Okay. So, do we get Newton? So here, these are the Lagrangian equations of motion. The Lagrangian is defined as the kinetic energy minus the potential energy with q dot and q. So these are generalized coordinates, so it should also work for Cartesian coordinates, and that it gives us Newton equation of motion. So in Cartesian coordinates, the Lagrangian is equal to the kinetic energy minus potential energy. And so the conjugate momentum of the position x is you take the partial derivative of the Lagrangian with respect to x dot, and we get the normal momenta in Cartesian coordinates. And the equation of motion is here, and that is exactly what you would expect from Newton's equations of motion. Okay, let's now take an example, and this example makes clear what is the advantage. So the question is, can we write down the equations of motion of this pendulum? This thing is oscillating around, but it's much more convenient to describe the equations of motions in terms of theta rather than x and y coordinates. So let's see how we can do that. So what we need to do is to write the equations of motion in terms of the length and in terms of theta. Well, here we used a fixed length, so the L will be a constant, but the theta does vary. Okay, so in Cartesian coordinates, the x coordinate is the length times sigma theta, and the y coordinate is L cosine theta. So if we have the kinetic energy, the kinetic energy is written here, and since you can see this can be easily written as in terms of L and theta dot, and this is the way you write the potential energy, and that is basically related to the height of the beat. If it's in the angle of 90 degrees is maximum the potential energy. If the angle is 0, the potential energy is 0, and this is exactly what is given with this equation. Okay, potential energy, kinetic energy. Okay, so now if we have the expression of the Lagrangian, we can define our conjugate momentum. So the conjugate momentum, which is the conjugate to the variable theta. So, and that is given by the partial derivative of the Lagrangian with respect to theta dot. So here we see the theta dot appearing, and it's ml squared theta dot. And if we have that, we can now write down the equations of motion simply. The conjugate momenta p sub theta dot is simply the derivative of the Lagrangian with respect to theta, and that is minus L sinus theta, which you simply get from this expression. So you see, we now have a very simple format of the equations of motion. So, and if we then substitute this one in here, you see, we basically get double dot, and here this is something we can easily solve. And you see, now we have a very straightforward and direct way to write the equations of motions in a format that it doesn't depend on the xy coordinates anymore, but you now have the equations of motion in these generalized coordinates theta and L, which is much more appropriate for this type of problem. And that is something which is really convenient. We're almost there. There's one more step I need to mention, and that is that statistical thermodynamics is done with the Hamiltonian, not with the Lagrangian. The Lagrangian is coming for the classical mechanics. So we can also do a Hamiltonian formulation of the dynamics, and that is a little bit more natural for statistical thermodynamics. So what we basically got with our Lagrangian equations of motion was a second order differential equation. But what we can also do is we can write a second order differential equations in terms of a set of two first order differential equations. And that's completely equivalent, and that is something you typically do in Hamiltonian dynamics. So this is the conjugate momenta. This is the momenta, and what we now and this is the equations of motion. So here we have the momenta associated with Q, and here we have the equations of motions. And this is giving us this second order differential equation. Okay, so basically what we need to do is we need to write this in terms of that. So this is basically we have the momenta, we have the time dependence of the momenta, and the differential equation is a second order differential equation. But what we can also do is we can write it in Q and momentum and basically write two first order differential equations. So what we need to do is we need to change the dependence. So we have a formula that depends on Q and Q dot, and we would like to have it dependent on Q and P. Well, this is something we actually have done in thermodynamics. And the reason we want to do that is because of the statistical thermodynamics is with momenta and positions. So the way you do that is a Lagrangian transformation. So we have the function f, which depends on x to n, and we have conjugate variables, which is defined as the partial derivative of f with respect to one of those variables. And the Lagrangian transformation is basically a new function, which is the current function minus the product of the conjugate variable and the actual variable. This all sounds abstract, but we have seen it before. And now this new function, and that is the theorem of a Lagrangian transformation, contains the same information, but only has a different dependence on the variables. Okay. So, classical thermodynamics, just to recap. So we have a function that depends, the energy, on the entropy and the volume, but we would like to have it depend on T and V. And that was something which was very convenient for our equilibrium conditions, because we had this small system in equilibrium with a thermostat. So we had this function, the energy, which depends on the entropy and the volume. And with this formula from the first law, so the conjugate variable of S is T. So a Lagrangian transformation is basically this original function minus the product of the variable you want to get rid of, the S, and its conjugate variable. So this is a coordinate transformation that has the same information. So E has the same information as F, but it has a more convenient dependence. So with this one, it basically depends on temperature and volume. So the F contains the same information as E, but we have this change of variable. And that is another way of looking at these auxiliary functions. It's just a Lagrangian transformation. So what did we have in our Lagrangian? And the Lagrangian depends on the conjugate, on the a generalized coordinate and its conjugate momentum, and we would like to have that changed in a slightly different way. And that was this, and that is why we introduced this Lagrangian transformation in this previous part with momentum and conjugate momentum. Okay, so what is the Lagrangian transformation? We have them depending on Q and Q dot, and this is the Lagrangian, and we would like to have a function that depends on Q and P, the momenta, and not on the time derivative. So what we can do is we can, like we did with the thermodynamics, we define our conjugate variable P, and we do this Lagrangian transformation. The only thing is to get the Hamiltonian. Normally you would do L minus that one, but this one, because of historic reason, the minus sign is different. So we have, but that doesn't matter. So it's P times Q dot minus the Lagrangian, and this is this Lagrangian transformation. So we can write this for the derivative, and you sort of see, you have Q dot P, this part and this part, and you see that those terms cancel because of the equations of motion. So what we have here, and we can sort of recognize these two terms, and these are now the equations of motions we want to get. And that is very similar to what we have done in classical thermodynamics. It's just a change of variables, and now you see the Hamiltonian gives you these two equations. And these are the Hamilton equations of motion. Okay, so the Hamilton equations of motions, will they also give us Newton's equations of motion? So here we have the Lagrangian. This is the conjugate momentum. So how do we get the Hamiltonian? We multiply the conjugate momentum with the actual position, and we do the Lagrangian transformation. So we take the Hamiltonian with a minus sign and add this term to it. Okay, so if you look at this, it's simply P squared 2m. It's the sum of the kinetic energy plus the potential energy. And the equations of motion that now follow directly from the Hamiltonian, this one and this one, and you see we get Newton's equations back again.